This is a lecture about neural network architectures, and we will focus primarily on neural nets for image problems. So specifically, we'll think about the standard problems for machine learning, such as classification and segmentation, but we'll also talk about image restoration problems like denoising and inpainting and deblurring. The types of architectures we'll consider will be multilayer perceptrons or fully connected nets, convolutional nets, residual nets, encoder-decoder nets, and autoencoders. So let's start with multilayer perceptrons, aka fully connected nets. So here what I have shown is an image of the architecture of a multilayer perceptron that was trained to solve an MNIST classification problem. So here the input layer is 784 different values, which you can think of as the pixel values of images of handwritten digits. Then under this architecture, then these 784 values are going to feed into multiple hidden layers. Each neuron in each hidden layer is connected to every single neuron of the previous layer. And then this is repeated all the way till the end until a softmax is taken, and then some probability distribution is created over the set of 10 classes. So under this architecture, the strength of this architecture is because it's fully connected, this net is a universal approximator. More or less any function can be approximated by such a net, and hence the function mapping images of handwritten digits to the class labels is something that this net should be able to handle. We can think qualitatively about what is going on with such a net as having this first phase, which is this part. That is the nonlinear learned representation of the data. And then this last phase is the, say, a linear classification. So in some certain sense, what the neural net is trying to do is to transform the input data in some nonlinear and complicated way into a linearly separable set of features from which a linear classifier can do a reasonable job. Now, some concerns about multilayer perceptrons. Once you have trained them, you can't alter the input size. After all, if you then decided to give it a larger image, all of the weights that were necessary to connect it to the additional layers would not have been trained in advance. Now, another concern about such a net is that no geometry about images is enforced in the net. And so we could say, well, what do we mean by geometry about images? Well, that means that, say, this pixel is near that pixel. And we know that in images, pixels that are very near each other are often highly correlated. For example, in the handwritten digits, like the stroke is a series, a contiguous series of pixels. Right? So with the multilayer perceptron, there's no idea that this pixel and that pixel are related geometrically. And really, such a net even has an idea of permutation and variance. One could consider, for example, this task 1, which is to say train a multilayer perceptron to output the class label given these images that are inputted. One could then consider another task, let's say task 2, where one takes a random permutation of these pixels and applies it to all of the images consistently, and then asks the multilayer perceptron to classify those as the digits 0 through 9. Because there's no geometry baked into the problem, task 1 and task 2 in this case are equally difficult. Now, certainly task 2 is not something that humans would be solving, and this might lead us to believe that multilayer perceptrons are a process that might be improved by paying attention to what humans or animals might actually be doing. And one particular feature of paying attention to would be the geometry and locality information within images. So with that idea, we arrive at the idea of a convolutional neural network, which is based on the presumption that local parts of image patches have a lot of information that can be captured. And then a network is built to reflect that belief. So here we're in a context of classification, and this, what's being shown is the image from this paper, LeCun et al. From 1998. And this is a paper where MNIST classification was being done. And in the network architecture here, there's a series of convolution layers followed by a nonlinear activation function. And then after this series of convolution layers is a series of fully connected layers. So really this architecture is a convolutional net followed by a multi-layer perceptron with the output being values that are going to act as a probability distribution over the 10 classes of digits. So this architecture is based on the idea that convolutional layers are well suited for images. And there are many ways that they're well suited for them. For example, as we discussed before, they can leverage the locality and geometry of images. So this is to say that, this value here of this feature map is based only on the pixels that are in a small section of the input to that layer. So then only those nearby pixels are really going to affect each other, and that's how locality and geometry is enforced. Now, in the convolutional net, there's translation invariance that's enforced, which is to say the weights that are applied to this square region are the same as the weights that are applied to that square region. They just head to different values within each of these corresponding feature maps. And so a convolutional layer pays attention to geometry, also enforces translation invariance. Now, translation invariance is an idea that we know applies to images. For example, a cat in this part of an image is the same as a cat in that part of an image. Now, additional benefits of convolutional networks are that they involve fewer parameters than multilayer perceptrons. One could view a multilayer perceptron as a generalization of a convolutional net, i.e. a convolutional net is like a multilayer perceptron where many of the values are set to 0 and many of the weights are shared. And having fewer parameters is good because it's easier to store these nets into memory, but also having lower dimensional optimization problems might be easier for existing optimization solvers to solve. Now, a nice feature about convolutional operations is that they can handle images of arbitrary size. After all, each pixel of output depends only on a particular size patch of input, and so then if you give a larger input, then you get a larger output. And so convolutions are an important tool in being able to deal with images of varying sizes, though we have to remember that because the multilayer perceptron itself cannot handle arbitrary sizes, then this classification net that's based on a CNN followed by a multilayer perceptron would not be able to handle nets, images of different sizes being input. For example, if you doubled the size of this image, then that would double the sizes of all of these images at this layer, and then that would require additional fully connected weights in order to connect to the next layer. And those would have to be learned by training on images of those appropriate sizes. Now, there are other architectures that follow the same flavor of a set of convolutions followed by a set of fully connected layers. For example, the famous AlexNet starts off with a series of convolutional layers, and then it also has multiple fully connected layers finishing off the net. So again, this first part of the net is like a nonlinear feature learning, or representation learning applied to the relevant images, and then this last layer is like a linear classifier. NotherNet, VGGNet, also has this architecture where the initial image is subject to a bunch of convolution layers and max pooling, which the down samples the images, and then leading into fully connected layers. Now here it's drawn as the fully connected layer has dimensions like 1 by 1 by 4096. That's like saying there are 4096 channels and a 1 by 1 image. All right. Now the next next thing we'll talk about are vanilla convolutional neural networks. And these are convolutional nets where there is nothing but convolutions. In particular, there's no like fully connected layers involved. And this is a sort of tool that might be very useful in the context of a variety of image restoration problems. So here's a figure of what a convolutional neural net architecture might look like. You have some input, you have a series of convolution layers, and let's say each layer preserves the height and width of these images. Each layer has some number of feature maps which could vary between layers, and then the output of this is also an image. So this figure here is from this paper, Lucas et al. 2018, which is a wonderful review of uses of neural networks for solving image restoration and other inverse problems. Now, a strength of vanilla CNNs is that they can retain the image size from input to output. This is achieved via padding. And what they can also do is operate on images of any size. So this is because all of the components are convolutions. Nothing stops a net being trained on images of a particular size from being applied to images of other sizes. Though, while we can apply such a net to images of arbitrary sizes, there are things we need to be careful about. For example, when designing such nets, we should be careful about receptive fields and image scale. And so by the receptive field, what we mean is, let's say there's one particular pixel in the output image. It's going to depend on some filter size within the previous map. That's going to depend on some larger set of spatial positions on the previous maps. And if we back that all the way up to the input, then that might, this pixel that was over here might be affected by this set of pixels that were in the input. So with such nets, we need to pay attention to the receptive field to make sure that whatever output we wanted at each pixel actually has information from all of the relevant input pixels that should affect it. And so if we do things like change the input size significantly, then that's not going to change the size of the receptive fields, but the problem we're solving may need information from the whole image in order to correctly modify the values at a particular point. So here, again, our point is that like CNNs, the pure CNNs, can operate on images of any size, but we should be very careful about the receptive fields of neurons, output pixels, making sure that they're sufficiently wide. And we should pay attention to things like the scale of the images that are being input to the system. Because if we trained a net on low resolution images and then handed it very, very high resolution images, then these receptive fields may be so small to not be able to make the meaningful image modifications we seek. So let's see some examples. So here's an example from this paper from Yann et al. In 2013 that does dirt removal on images. So here, what's being shown is here's an original image right here. And then this image was, a net was trained in order to remove dirt from these images. So here's an image with dirt synthetically added, with snow synthetically added, and with scratches synthetically added. And then this CNN was able to output an image that removed the dirt successfully. And even in a case of an image where there was no dirt, it preserved that image. And what we see is that this net that was trained to remove dirt doesn't do things like removing snow or removing these scratches. And that's natural because we trained this net in a supervised way to solve a particular task. We should not expect the net to magically solve other tasks, even though they may be quite meaningfully related tasks in our opinions. And so this was an example of a pure CNN being applied to do some image restoration. Here's another example in the case of blind deconvolution. So here the one has an input image, which is like a blurred version of some image, and you don't know what the image being taken was, and you don't know exactly the way it was blurred. For example, there could be a Gaussian blur, there could be a motion blur, there could be combinations of these blurs, and we need to remove them. So this paper by Hradish et al. In 2015 had a 15-layer convolutional neural net where they were successfully able to solve blind deconvolution relative to state-of-the-art baselines at the time. And here are examples of input-output pairs from that. So again, this net involved 15 layers. They were all convolutions. Now, another important category of nets is based on residual blocks and skip connections. And so a residual block is as follows. So let's say we have some input image, and then we do some convolution or something to get a set of feature maps. Now, instead of just applying one feature map to another via convolutions, we might do a couple of convolutions, and then we might add this output to the input of this block. And so this is something we call a residual block. We might have multiple residual blocks in between the input of our net and the output of our net. Now, another way of visualizing it is, so you have some input values x, then one computes some function f of x using this sub-network. So this is kind of like a network within the network. And then one adds f of x to x in this block. Now, it's important when working with residual blocks to make sure that enough computation is actually performed in the residual block to be useful. And for example, in the original ResNet paper by He et al., they noted that if this residual block only had one layer, then it wasn't particularly effective, and one needed 2 or more layers within the residual block to give performance gains. And the argument for that was, with one residual block is more or less like a linear function that you're learning, like the identity plus some matrix times x, whereas with multiple layers you have some complex nonlinearities that are involved that can appropriately modify the input to this block. And so the ResNet led to a very deep architecture for classification. So here is this architecture. It had a series of blocks and these residual connections. Note each block has 2 layers within it for the reason we described before. And more or less this architecture is a set of convolutions followed by a fully connected layer. So this is again like we saw with the classifiers before. There's some representation learning going on. Representations are learned, and then classification decisions are made. So residual blocks are an important tool in the history of deep learning, and in particular, they allowed for increased depth of neural networks. We saw before that in multiple problems, like relatively nets with relatively many layers, like 10 or 15, were performing quite well at image processing tasks and classification tasks, and this residual architectures allowed the ability to increase the number of layers even more. So with increased depth comes multiple benefits. For example, their large receptive fields are possible when you are able to have depths that are, or nets that are very, very deep. And then there's a consequence of that, which is that smaller filter sizes could be used. That is to say, instead of having one filter that might be 11 by 11, one might have a series of 3 by 3 filters over many layers. And this allows for a savings in parameter count. One could prefer to have more layers with smaller filter sizes while achieving comparable receptive fields. Here's an example of a ResNet that was used for the image processing task of super resolution in this paper by Ledig et al. In 2017. In this task, one is given a low resolution image like this, and one wants to find the high resolution version of it. Or you could think of this as you have a photograph, you rescale it to be 4 times smaller, and then you want to rescale that to be 4 times bigger. And if you do that naively or with a standard analytical method like bicubic interpolation, then you'll get something blurry like this, and we want to do better than that. So with the super resolution problem, like a residual net is a relatively reasonable, gives good performance for this task. This is the network used in this particular paper. And what we see is, again, there are skip connections, and there are multiple layers within each of these residual blocks. And so it has the same flavor as the ResNet for classification before. And one big takeaway message that we get is that ResNets are good at successive refinement of images. So this could mean that at each layer of the ResNet, these edges are sort of successively getting sharpened, or perhaps in a denoising problem where one's removing noise from an image, each successive layer may be removing just a little bit more noise than the previous layer. One could apply this idea of like learning residuals in a different way, even for the same problem of super resolution. So in this paper by Kim et al. In 2016, the idea was to train a net that predicts the residual needed to do super resolution. So again, we have some low resolution image here. We want to come up with a high resolution version of it. And so we will build a convolutional neural net using conv operations and ReLUs in this case to build up exactly the residual we want, and then we're going to add it to the original image. Now the idea of this is based on the following premise, that like, learning a residual might in some cases be easier than learning the full mapping itself. And as an analogy to this, we could think, suppose we have a painting which has some crack in it or some error that was added to it, and we want to fix that crack or fix that error or otherwise restore this painting. Then we could say, all right, we will look at the painting as a whole, and then we're going to infer what small modification we need to fix the painting to be self-consistent. That sounds like an easier task than studying the painting, identifying what's wrong, and recreating the entire painting from scratch. And that's roughly the difference between this learning a residual and learning a net which directly outputs, say, a high resolution image from the corresponding low resolution input. Our next type of net that we'll talk about is an encoder-decoder net. And these have the following structure. There's an image, which is input to this net. Then there's going to be a series of layers which downsample this image and process it using convolutional operations usually. Then there's going to be a point or a series of layers that are a bottleneck where there are relatively few parameters. And then there's going to be some decoder part which takes the values, the activation values in this bottleneck, and then upsamples these to an image which is the desired output. And here the desired output could be the same or different than the input of this net. So in a certain sense, what is going on here is that the encoder converts an image to some set of latent variables, which we might call a code. Well, that's why it's called an encoder, because it takes an image and it encodes it into some code. So then there's a decoder, which takes a code and then generates some image from that code. The design of these nets is usually that there's a bottleneck in the middle, and that bottleneck has typically low dimensionality. And the reason for this is that the bottleneck forces the net to gain some kind of semantic understanding of the image. So that is to say, since it has relatively few degrees of freedom, yet it has to express the relationship of these input images and output images as well as possible, it is incentivized to use those degrees of freedom to capture the primary features of variation within a training data set, and those features of variation hopefully are sort of semantically meaningful. So these nets are particularly well suited for tasks that have high semantic content, meaning they need to pay attention to the actual content of what's in an image, like the objects, the meaning of things, as opposed to just a set of pixel values. In contrast, tasks which may have low semantic needs include something like denoising or super resolution, where you could do that without understanding exactly what the image is of. Here's an example of a paper by Patrick et al. In 2016, where an encoder-decoder net was used for inpainting. So in this problem, one's given an image, and then let's say there's this block of pixels that's missing from that image. And what we need to do is fill in those pixels. So if those pixels are missing in this big block, this requires a semantic understanding of the image. If these pixels are randomly spread out throughout the image, then that doesn't require as much of a semantic understanding of the image itself. So in this paper, what they did is they trained a net where there was some encoder, and this had a convolutional neural net structure, very similar to AlexNet. Then there was, within the bottleneck, a learned set of fully connected layers within each channel. And then there was a convolutional decoder to upsample these decoded features into a particular image. And then that image is the output of the net, and it's trained in comparison to what the actual cropped segment of this input image was. And here what we see is that this net seems to do a reasonable job, where it can be tested on these images down here, and it fills them in a semantically reasonable way. Now, of course, the nets aren't psychic, and this, the way it fills in the sailboat might not be fully accurate, but this is a very reasonable performance for inpainting. So again, here the idea is that because the encoder-decoder structure captures the semantic understanding of images, it may be a useful structure for solving this semantically difficult inpainting problem. Now, if we just had the encoder-decoder structure, the bottleneck results in a loss of dimensionality, and then upon reconstruction, that may lead to a loss of detail in the decoded images. And so there's an exciting fix to this, which is to include skip connections, and this yields a famous network called a UNet. So the UNet is this architecture depicted here that was created for segmentation of biomedical images. So that problem is, say, one has an input, which is this image, and one might want to identify where are all of the individual cells within that image. What's shown in part B is a sort of ground truth labeling of where these individual cells are, and what's shown in part C is the output of their neural net. So this task, given an input, basically label each pixel as what type of pixel it's in. Which cell is it in? Is it a boundary pixel? Is it not a boundary pixel? This sort of thing. So here, this image A is the input to this net, and then the output segmentation map is so the labels of each individual pixel. So this UNet captures both an autoencoder structure and so it has skip connections. Here we see the encoder-decoder structure we see represented because this input is squished down into this bottleneck, and then upon upsampling and convolution layers, these skip connections are added in. Right. So the strengths of UNets, particularly for the segmentation task, are the semantic understanding needed for segmentation is achieved by the bottleneck, but the skip connections also preserve detail. And in this problem, one needs to identify both where are the individual cells or the regions of interest, but then one also needs to pay attention to the exact boundary of those. And that's where the details are important coming from the skip connections. Now, a special class of encoder-decoder nets are autoencoders. And here we're actually changing the context in which we're in a bit. Our context is now unsupervised representation learning. So instead of having a series of before and after values, for example, images and their classification labels, or low resolution images with their high resolution counterparts, here we just have a collection of images. And the goal is to learn good representations of these images so that we can do other things downstream with them. So an autoencoder will have the following structure, right? There's some input, that's some image that's input. There's a series of, say, convolutional layers, and then there's a bottleneck right here, and a series of upscaling and convolutional layers to give an output. And the goal is to find a net that makes the output the same as the input. So that is to say, when you hand it X, you want to get out something as close to X as possible. And so this is unsupervised because all it requires is a set of images. It doesn't require any labels or responses to those images to be known in advance. There are a couple of types of autoencoders, like denoising autoencoders and compressive autoencoders. A compressive autoencoder is one where this code itself is of lower dimensionality than the input to the net. And if the net successfully approximates input images and output images using lower dimensional code as a bottleneck, then it is learned a concise representation of those images. And with that representation, you could do something like compress those images. So here's an example from Tice et al. In 2017 of a compressive autoencoder, where here is the input. There's a series of convolutional layers. This actually has some like residual skip connections. Then this output of the encoder gets rounded, because after all, these images need to be stored, and one pays attention to the amount of bits that it takes to represent the image, then this results into a code which could be transmitted to someone else. Now, once that code is received, then it can be used for this decoder network, and it has this like residual block structure leading out to the output image. And so what the authors here showed was that their method, this compressive autoencoder, was able to outperform JPEG and JPEG 2000 at comparable bit rates. And here we can see there's a bit more fine detail that is reconstructed with the compressive autoencoder than with these JPEG standards. And so again here, the idea is that because the autoencoder was able to represent images with a code of lower dimensionality, that could be used for compression and storage of images. Now there are other things that you can do with the representations from autoencoders. And here's one neat example that is used for superresolution. So in this paper by Zhang et al. In 2017, they had a series of low-resolution images and high-resolution images. For each of them, they trained an autoencoder. So here for the low-resolution images, they trained this autoencoder, and here's its bottleneck, so like the latent code for each of the images. And then here for the high-resolution images, they trained a different autoencoder, and then they have the latent codes for those images. Now, if we want to train a net in this case, now in a supervised setting, to map from low resolution to high resolution images. So one takes this first half of this autoencoder for the low resolution images. One then has some deep neural network, maybe multilayer perceptron, for example, to try to map the latent codes from the low resolution images to the latent codes of the high resolution images. And then with that, one can output an estimate of the high resolution image. And so then when one completes this testing phase, then one is given an image, a low resolution image to which you seek the high resolution part, then you compute the representation of that image given the trained autoencoder. You then apply this neural network that was trained to map it to the representation within the other autoencoder, and then you use the second half of the other autoencoder to output the estimate of the recovered images. So here the point is that once you have representations of images that are learned in an unsupervised way, you can then use these representations to solve a variety of problems, supervised or otherwise. And once you have those representations, often then you can find interesting and important things to do with them. So what I want to do is conclude with one last idea. And we've talked a lot about a variety of neural network architectures. And this last idea is you could consider sparing nets from learning things that you already know. And we've already seen examples of this so far, for example, with a convolutional net. Right? We know that there's translation invariance within neural networks. A cat in this part of an image is the same as a cat in that part of an image. And so we can teach that to the net by using convolutional layers to which bake in that translation invariance. So that is an example of us enforcing the knowledge that we have. If we didn't do that, we could still learn it. Right? For example, we could take a multilayer perceptron and then explicitly have to teach it that objects in this part of the net, if the same cat is in this part of the net or that part of the net, then the output should be the same. We might have to do some tricks to actually get that net to behave well. For example, we might need to do a lot of data augmentation and take the images in our training set and then shift the locations of pixels within it to make sure that the decisions are robust to the locations of particular features. And so that's just an illustration of if we don't enforce what we know, we might have to spend a lot more data teaching the net things that we already knew. So this idea of spare nets from learning things that you already know, a different way of saying it is like fully end-to-end trained networks for certain problems might not be the best approach. And so let's see some examples of this. So one example is the problem of compressed sensing. So this problem goes as follows. You have some signal, let's say it's an image, which here we vectorize just in a particular, just to be a column vector, but it's all of the pixels of a single image. Then one takes measurements of this image by applying some linear operator phi to it. This could be you observe random combinations of pixels. It could be you observe certain pixels. It could be you observe certain Fourier modes, but you have some linear measurements on this image, and you get a measurement vector y. And here the important thing is that y is usually of lower dimensionality than x. And your goal in compressed sensing is to recover the image x from the measurements y. Now there's a whole field of compressed sensing which has tools to do this, but we could consider building a neural net to do this. After all, the neural nets are universal approximators, so they should be able to approximate whatever function we would solve by other methods to go from y to x. And one could consider building a net that takes y as input and then outputs x. But this isn't typically the best way of solving such a problem, because after all, this requires having the net learn how to go from measurements to images and then perhaps how to manipulate within images. So in this paper by Musavi and Baranek in 2017, what they did is they took the measurement vector y, they applied phi transpose to it. So remember, phi is a matrix that goes from the dimensionality of x to the dimensionality of y. So phi transpose is a matrix that goes from the dimensionality of y to the dimensionality of x. So here, applying this linear operator, we get an image. Now, this image isn't very good, or else we wouldn't really need any other approach to solving this problem. And typically, these images have a lot of artifacts in it that are undesirable, and that's why fancier methods are needed. So instead of doing fancier additional analytical methods, what this paper does is that it trains a neural net to take as input these estimates of the recovered image and trying to estimate from them like better estimates of the recovered image. And they do this through a series of convolutional layers. Okay. So the point here is again that instead of training the net to take y and then output this desired image, they did particular operations to get an input image already and then train the net to operate on that. So this knowledge of how to go from y to this input image, this encodes like understandings that we as humans have about the measurement process that was taken here. Right? We could encode this information in multiple ways. For example, instead of using phi transpose, one could use the pseudo-inverse of phi or other operations in order to get even better proxies for the image that we're seeking. But nonetheless, from being experts in this field of image recovery from compressed measurements, we can bake in that expertise into a system so that our neural net doesn't have to learn that part. Now, as an example of an important application of this is the problem of MRI reconstruction. So here we can think of this as like we have an image, let's say like the true image of some of the biomatter that's in the MRI scanner. And then linear measurements of this is taken, and those linear measurements roughly correspond to individual modes in Fourier space that may be scattered around the frequency domain. So what's shown here on the left is, say, a true image reconstruction if a complete set of measurements is taken. But in MRI, one wants to recover images from as few measurements as possible because this leads to people sitting in an MRI machine for less total time. So one could consider building a neural net which takes the measurements of the MRI and tries to directly output the MRI image. But that's kind of like the problematic way of solving the compressed sensing problem we saw before. So instead, one could do things like initially begin with inverse Fourier transform to get a rough approximation of this image, and then could train neural nets to take this rough approximation of these images and output higher quality images from there. Now, these methods may be limited in performance by the artifacts that are typical in these sort of initial proxies, and additional advances could be made, for example, by doing MRI reconstruction not in pixel space, but in Fourier space. And then once one thinks to do something like that, then we need to think about, well, what are the neural network architectures that are appropriate for Fourier space? After all, we spent a whole lot of time just now talking about convolutional nets and how they're great for image and pixel domain, but they might not be great for the Fourier domain. And developing methods for that domain is something that is ongoing research.